All right, so let's look at the power factor. Earlier we discussed that in the active power or average power, which is given by P is equal to VRMS IRMS cosine of theta minus phi. This theta minus phi, where theta is the phase of the voltage and phi is the phase of the current. So theta minus phi is the voltage difference between the phases of voltage and current, which is also the phase of the impedance. Remember, impedance is the ratio between the voltage and current. So this cosine theta minus phi plays an extremely important role in the power management and the bill that you pay to the power company. Um, of course, all of you know that the power meter that you have at your home, it is a watt hour meter. It calculates how many watts of energy you are using or power you are using every hour. So it is calculating energy, watt hour meter. Uh, so it is calculating energy usage uh, and energy corresponding to the active power or average power. Now, cosine theta minus phi, which is the power factor, what is its significance? So power company is sending you current based on how much load do you have at your home, and watt hour meter can only measure the active power. Now remember, the active power is only dissipated in the resistive part of the circuit, not the reactive part, the resistive part of the circuit. So if your load is purely resistive, then the phase difference between voltage and current is zero. Through a resistor, voltage and current are in phase. That means cosine zero, that means your power factor will be zero if you have resistive load. What would that mean? That means the power is going to be maximum, which will be VRMS times RMS, IRMS. Because remember, cosine goes from what? 0 to 1. So when cosine theta minus phi is 0, cosine of 0 is 1, that's the maximum power that you can consume. Or in other words, you will be paying the bill of the true power that the power company is sending you, that is the current. Of course, voltage always remain constant. You have 110 volt RMS, that's the standard, right? It all depends on how much current you are pulling. So if you have purely resistive load, whatever current you're pulling, you're going to be paying the bill for that. Now assume that you have some inductive load. That means cosine theta minus phi is not going to be 1. It is going to be between 0 and 1 somewhere. What does that mean? That means your total active power, when you calculate through this formula, since this will be power factor will be less than 1, more than 0, less than 1, that means your active power is going to be less than if you are calculating for purely resistive load, right? So assume that, for example, your resistance is 100 ohms, right? And of course, and your reactance is 0. So if your resistance is 100 ohm, cosine of course is going, cosine of power factor will be 1, and your power is going to be, active power will be maximum. Now observe, if you say your resistance is R plus jx, and let's say you have 100 plus j50 ohm, right? So what is going to happen? What is going to happen is your phase angle. So what will be the phase angle? Your phase angle is the phase of impedance. So this is your impedance, right? So the phase of impedance, what is the phase of impedance? Angle of Z is equal to arctan of imaginary over real, inductance over resistance, 50 over 100. So that means this phase angle is going to be less than or is going to be cosine is going to be less than 1. Phase angle is going to be more than 0 but less than 90 degrees. So the current that you're pulling, so if you have inductance, let's say you have motors, you have a home industry and you have bunch of motors, and to establish the field in the motor through electromagnets, of course you have to pull a lot of current. But this watt hour meter that you have at your home, it cannot measure that. It can only measure the active power. Any power that is going towards inductor to establish the field is the reactive power. So what is happening is you are pulling a lot of current from the power company, but you're not paying the bill because the power company is not measuring it, and in fact your power factor is less than 1. So your power that you're pulling, the actual power that you're pulling or actual current that you're pulling, it is not going to measure that. It is going to measure less than that because of the smaller power factor. All right, so of course power companies know about it. So for normal consumer, of course at home we don't really have home industry motors and stuff. Most of our load is resistive, so they do the adjustment in the meter and they know how much an average house should be paying. Now if you do have in an industry, then what they do is they do power factor correction, or they ask you to do power factor correction. So they're going to make some correction in the meter and they will say, well, if your meter is reading this, this is the actual bill that you will have to pay, because of course the meter cannot record the extra current that you're pulling to power up or excite the field, because your power factor is less than 1. So if you have motors, you have inductors, generally if you have for corporations and stuff, mills and big motors, generally what they do, they put basically power the capacitor banks in parallel to the motors. They put capacitor banks in parallel to the motor. So what happens is, let's say this is the motor, this is the motor winding, this is the motor reactance and the resistance, let's say, and this is your 110 volt supply or 220 volt supply, whatever AC RMS value. So what happens is, without the presence of this capacitor, all the current that is required by the motor will be coming from the line. Now once you add this capacitor, then the capacitor will start supplying some of this reactive power. Remember earlier I mentioned that reactive power for the capacitors is negative, and reactive power is what? Vrms IRMS cosine of theta minus sine of theta minus v, sorry, not cosine, sine of theta minus v. Let's clean this up real quick. Okay, clean enough. Okay, so it is sine of sine of theta minus v, right? So for capacitor, of course, the theta minus v is negative 90 degrees. So we discussed that it is a negative Q. Negative Q means that on average the Q will be coming out of the capacitor. So QC is negative, and QL is positive because theta minus C is a positive value, 90 degrees for inductor. So the total power that will be total reactive power that will be supplied by the source will be QL plus QC. QL is positive, QC is negative. So the total power is going to be smaller because some of the power that was required by the motor is now supplied by the capacitor, and that will change the power factor. That's called power factor correction. So it will basically move the angle of impedance towards 0 degrees. So cosine value is gonna increase, which means basically what does that mean? That this QL in parallel to QC is gonna become a smaller value as compared to R. So if R is large in R plus JX, if R is large, you have mostly resistive load. If X is large, you have mostly inductive load or reactive load. So when you connect this Q in parallel with L, basically you are making X is small. The equivalent X is small. QC in parallel to QL. Not QC, sorry. C in parallel to L, or XC in parallel to XL. But in other words, some of the current will be supplied and some of the power, reactive power, will be supplied by the capacitor. Rest of the power and current will be supplied by the line. And there's an example that we're going to discuss as well. Now, if reactive power supplied by the capacitor is more than what is required by the inductor, then it will fully support the inductor, and rest of the power is gonna go back to the line actually. So the line current is just gonna get even smaller in that case. All right. So this is the concept of power factor. So the power factor is basically cosine of theta minus phi, and power factor gives you an idea, first of all, how inductive, resistive, or reactive your load is. So if theta minus phi is 0, your load is purely resistive. So power factor is 1 for resistive load. If theta minus phi is between 0 and 90 degrees, then your load is inductive, and cosine theta minus phi is going to be less than 1 but more than 0. If theta minus phi is 90 degrees, then power factor will be 0 and your load will be inductive. And likewise for capacitive impedance, theta minus phi will be between 0 degrees and negative 90 degrees. And remember, cosine of negative angle in the fourth quadrant and cosine of positive angle in the first quadrant, both values are positive. So you won't be able to actually distinguish if your load is reactive, inductive reactance or capacitive reactance. That's a problem. So to deal with that problem, we add lagging or leading power factor. It is extremely important that you add either power factor is lagging or power factor is leading. What does that mean? That goes by if current is leading the voltage or current is lagging the voltage. So in your inductive load, current is lagging the voltage. So the power factor, let's say if I say power factor is 0.7 lagging, if I just say power factor is 0.7, then you will not know if the power factor 0.7 is due to the inductive impedance or capacitive impedance, because again cosine of negative angle in the fourth quadrant and cosine of positive angle in the first quadrant both can give you 0.7. But if you add lagging, then you will know that this is due to the inductive load. And if you add leading, that means the power factor is due to the capacitive load, because current leads voltage in the capacitive loads. All right, so this is the story of power factor. Power factor's importance is that it tells power company, it tells you how much bill do you have to pay, because the higher the power factor, the more resistive your load is, and the actual current that you're pulling, you're gonna pay the bill of that. The lower the power factor, you are still pulling a lot of current, but your wattmeter will not be able to record all that energy that you're pulling, because cosine value is going to be small, and power company will be giving you basically free energy, and of course power company is not going to do that. So there is a lot of of course this is an introductory course of power system, but power factor plays an extremely important role in power systems. Power companies do power factor correction, especially for the industries. Also they recommend to industries that you have to use the capacitor banks to basically do the power factor correction and reduce the load on the line to pull less current. And if they don't do that, then of course there are penalties and stuff that they can also impose if the power factor correction is not done. All right, one more thing about theta minus phi. So we discussed theta minus phi is the phase angle difference between the voltage phase and current phase. This is also the phase of the impedance. Also, when you're calculating theta minus phi, you can also calculate that using arctan of Q over P. That is the reactive power over active power. Why Q over P? Because remember, Q is right here. I don't have to rewrite it. Vrms Irms theta sine theta minus phi, and P is Vrms Irms cosine theta minus phi. So when you plug this here and plug this here, Vrms and Irms will cancel out each other. Both will be in the numerator and denominator, and you will have sine theta minus phi divided by cosine theta minus phi, which is what? Tangent theta minus phi. So arctan and tangent will cancel each other, and you will be left with theta minus phi. So the angle of the power factor, theta minus phi, can also be calculated using arc tan Q over P. So either you can do arc tan Q over P, you can do arc tan X over R, which is the angle of impedance, or you can simply do, you can simply take the difference between the phase of the voltage and phase of the current. This is your active power, apparent power times cosine of theta minus phi, right? This is your apparent power S, and I show the magnitude of complex power as the apparent power. So active power can also be given by apparent power times power factor, apparent power times power factor. And Q can also be given by apparent power times sine of theta minus phi, or sine of, remember theta minus phi is what? Power factor. Cosine theta minus phi is power factor. So theta minus phi can be given by cosine inverse of power factor. So Q can also be written as S sine of cosine inverse of power factor, right? That you can also write Q like that. So all are connect, the same form, but you can write whichever quantity is given to you. So let's look at this example, and this example is pretty straightforward. 10 ampere current is being pulled by this motor connected to 110 volt RMS, 60 hertz line. Power factor is 80% lagging. So generally power factor is given in terms of percentage, because remember power factor can only go from 0 to 100%, 0 to 1, either lagging or leading. It cannot exceed 1, it cannot go below 0. Determine the active and reactive power. So active power is supply voltage ES times current times the power factor, as we just discussed, 880 watt, and reactive power is ES times I sine of cosine inverse of power factor, as I just explained. So 660 volt ampere reactive. Another example, and in this example, as I was mentioning it to you, we are adding a capacitor bank in parallel to the same motor that we have in example 7.2. So this is the same motor that is pulling 10 ampere at 110 volt RMS, and it has 80% lagging power factor. So now we want to do the power factor correction, and you will see that we want the load on the line to be reduced. That means we want the line not to give all 10 ampere current to the motor, but some current should come from the capacitor. And that's exactly what's going to happen in this. So we are putting a capacitor over here, and this capacitor is 50 microfarad. This motor and power supply is the same as in the last example. So motor still has 80% lagging power factor, and it will still be pulling 880 watt of active power and 660 volt ampere reactive power. So motor is the same. We will see how much power is being now delivered by reactive power. Active power, since there is only one source that or component that is dissipating the active power, all this active power has to be supplied by the source. Of course, capacitor cannot dissipate active power, it's only reactive power. So 880 watt will be supplied by the source, but out of 660 volt ampere reactive required by the motor, we will see how much is supplied by the capacitor, and rest of it will be supplied by the source. So that's what we're going to look at in this problem. So first we calculated the reactance associated with your capacitor. So reactance came out to be 53.052, frequency is 60 hertz. And the reactive power of the capacitor we calculated ES square. ES is the voltage across the capacitor. ES square magnitude divided by the magnitude of the reactance. And since capacitor reactive power is negative, I'm just adding a negative sign over here. So it is producing negative 228.08 volt ampere reactive. So the total reactive power by the line will be reactive power of capacitor plus reactive power of motor. So reactive power of capacitor is negative 228, reactive power of motor of 660. So total reactive power supplied by the line is 431.92 volt ampere reactive, as opposed to all 660 volt ampere reactive that was being supplied by the line in the previous problem because there was no capacitor bank. So observe the reactive power supplied by the line. Here it went down from 660 volt ampere reactive. Alright, what is the apparent power of the line? That's going to be the active power of the line is square plus the reactive power of the line is square root of that, 980.28 volt ampere. And then we're going to calculate what is the new line current. New line current can be found out by apparent power divided by ES, because apparent power is simply ES times IS, volt ampere. So we calculate new current, it's 8.91. Observe, went down from 10 ampere to 8.91 ampere. So we are reducing the load on the line. And then the power factor of the line. The new power factor of the line is what? Power factor can be calculated by active power divided by apparent power, because again active power is apparent power times the power factor. So the power factor of the line is 89.7, approximately 90% lagging, and it has improved because before it was 80% when you only had the motor. So it is going towards 1. It is improving. That means now power company can start charging you the correct bill based on how much current you are pulling. So that's a really good example. Alright, active sources and loads. I'm just gonna cover all of this in this video. Active sources and load, basically if and again this goes back to your circuit analysis. What is an active source? What is an active load? So if your source, if the positive current is coming out from the positive side of the source, that source is called active source. That is, that source is supplying active power. And if any device positive current is entering into the positive terminal of that device, that component is called active load, because it is consuming power, active power. So that's what active source and active load is, right? Alright, system comprising of several loads. If you have bunch of loads, see, anytime you connect anything with the power system, remember our voltage, home consumer, our voltage is standard 110 volt RMS, right? So anytime you connect anything to your socket, 110 volt RMS is going to appear across that. What does that mean? If your voltage across the component is same, how do those components are connected? They are connected always in what? Parallel. So anything that you connect with the socket, it will always come out to be parallel to each other, with the power supply to be 110 volt RMS or 159.5 volts. So if you have a system to which you are connecting multiple loads, some loads are resistive, some loads are reactive, and under reactive loads some loads are inductive, some loads are capacitive. The total power that is supplied by the system, by the line, is going to be simply sum of all the resistive power will be the total active power supplied by the line. Sum of all the reactive power is the total reactive power supplied by the line. Now, when you're calculating the reactive power, adding all the reactive power, you just have to be smart to calculate it positive for the inductive type of load and negative for the capacitive type of load. That's very simple. So if you look at this example 7.4, you have a power system 220 volt RMS, which is in Europe and Asia and other parts of the country, other parts of the world. And you are connecting different loads to that system. Resistive load, 3 types of resistive load, 3 types of inductive load, and 2 types of capacitive load. So the question is asking you what is the total active power absorbed by the load. You add all the active power, total reactive power supplied by the line. So you add both the reactive power, keeping the positive with the inductive and negative with the capacitive, and that's what I did. So total reactive power supplied by the line is negative 5 kilovolt ampere reactive. That means that actually the source is receiving the power instead of power going out of the source, reactive power, that is. The source is receiving some of the power because the capacitor are producing power more than what is required by the load that are connected in parallel, reactive power we are talking about. So the reactive power is coming back to the source, which goes basically in energizing the field of the generators that are producing the power for the line. What is the apparent power of the system? Again, apparent power is, remember, apparent power is the magnitude of the complex power, and complex power is P plus JQ. So apparent power is square root of P square plus Q square. So you calculate that. And line current. And line current you calculate. Apparent power equals Vrms IRMS. So line current IRMS is S over Vrms, S over ES. Power factor of the system is calculated using P is equal to apparent power times power factor. So power factor of the system is 0.978 leading, because the Q is negative. That means your load is, total load is capacitive load. So for capacitive load, power factor will always be leading. Make sure remember that, right? So 97.8% leading. Alright, another example I'm showing you, and this example is pretty much what you did in circuit analysis. So you have a motor with inductance 26.526 millihenry, a capacitor which 265.26 microfarad, resistance of 2 ohm, and your source voltage is 200 volt RMS at 60 hertz. So first, and we are asking what is the complex power of the motor, what is the complex power in this motor. So you calculate first the reactance of the motor, reactance of the coil, that is, which came out to be J10 ohm. Impedance of the motor, since both of them are in series, you add them together. You calculate motor current, right? ES over ZM. Of course, this is a complex quantity because you are in the phasor domain. And then you calculate the complex power of the motor. ES times IM complex conjugate. It came out to be 769.23 plus J3846 volt ampere. So this is your active power of the motor, which is dissipated here, P, and this is your reactive power of the motor, not I. Make sure don't put I, because reactive power is a real number. So 3.846 kilovolt ampere reactive is dissipated in L. Okay. Reactive power of the capacitor, we calculate reactive power of the capacitor. Simply capacitor voltage is ES. So first we calculate capacitor current, or you can, you can directly calculate it as ES square magnitude divided by magnitude of XC. You can also calculate that. What I'm showing you is I'm calculating the current of the capacitor, and then I'm using the reactive power formula, ES times IC times sine of phase of ES minus phase of IC, and of course that is negative 90 because you have J. Remember, J correspond to negative 90 degree. This is J in the complex plane, in the S plane. This is your real, this is your negative real, this is your imaginary, this is your negative imaginary, and of course 90 degree correspond to J, which is on the imaginary axis. So negative 4 kilovolt ampere reactive is the reactive power of the capacitor. Of course, sine of negative 90 is negative value. Total reactive power of the line, you add the capacitor power reactive and the motor power reactive. It is negative, that means your system is your system reactance is mostly capacitive. Apparent power of the line, like we calculated last time, we calculated that, and line current and the power factor. Again, the power factor will be leading, 98% leading, because your Q is negative, that means your load is capacitive load. And I'm assuming this will finish the chapter.